Hi, I'm Joe Kimbrell. This is the final demonstration of fast queuing policies for computer communications. I'll start with just an introduction, going over the motivations, overview, and problem statement from the paper I selected. So quality of service is an important parameter in any network protocol design and is becoming more and more important as we move to more wireless communications. A few of the parameters include maximum jitter, delay, loss, or even minimum bandwidth. It's important to note that quality of service can change depending on the application at hand. Say you have a video conference, you want to emphasize packet delay, whereas a cell phone might require an emphasis on power consumption. Real-time applications may require optimizations on the fly, so we need a framework for customized designs of robust network protocols. So we need a better framework, but how do we accomplish this? The paper suggests abstracting the network protocol as a queuing policy. This allows the application of queuing theory to the problems in the network protocol, and also allows for the generalization of protocol designs via cost functions. For queuing theory, you can use the Markov process and make use of the stationary distribution to obtain a queuing policy. As far as optimization, you can find the best queuing policy for given quality of service requirements. Now, before we go on, I want to compare the math and the reality that's presented in the paper. So when I talk about a cost function, I mean some sort of quality of service requirement. Probability matrix is the queue or the system we're analyzing. The stationary distribution is our queuing policy. Threshold is our quality of service tolerance, and the total cost is our optimized quality of service for the entire system. So the purpose of the paper is to abstract network protocols as queuing policies, as mentioned before, and to leverage queuing theory to improve these policies based on cost functions as you see on the right. So for the project, I decided to generate the queue from random input and output data, run the algorithm provided in the paper on the queue, and hopefully obtain an improved policy. And this improvement will be noted by recording the reduction in total cost of the policy. So these are the steps of the overall algorithm. You start by generating a random vector of inputs and outputs, and you generate a queue matrix from step 1, according to the matrix function defined in the paper and shown on the right. The A terms are the input probabilities, while the S terms are the output probabilities. Next, we calculate the stationary distribution of the probability matrix formed in step 2. Next, we combine the stationary distribution with the cost function to become the total cost of the system. We then run the algorithm that will be discussed in a few slides to determine a new probability matrix, and repeat these steps until a threshold is reached, or in many cases, we time out and no optimization can be done. Once these are all done, we report the final cost and stationary distribution. Alright, let's look at the MATLAB. So I'll be going through all those pseudocode steps by looking at the MATLAB code that I've written and combined to make the overall application. So we start by generating a random tri-diagonal probability matrix. This implements the initial probability matrix equation that was shown in a few slides back and is also shown here. Again, A is the input probability and S is the output probability. You decided to use MATLAB's random number generator to generate these inputs and outputs because in the real world you might not know what these are going to be. Next, to generate the cost functions, and I decided to use the cost functions that were mentioned in the paper with some slight modifications. So the first one, the authors stated that it could represent a reduction in energy consumption with lower sending rate. It's Case 2 could be an operating point that reduces power consumption. And we also have case 3, which is approximately linear. Next, we calculate the stationary distribution. And I actually was able to obtain the main calculation code from the MATLAB MathWorks repository. This code uses a state space reduction to calculate the stationary distribution. However, I added conversion from symbolic to numerical format because the original coders had written this in symbolic notation. So in order to actually use it in my own methods, I needed to have it in numerical format. I also needed to mask negative states because sometimes MATLAB would report back a -0, and this was done to prevent error propagation. Next, I calculate the total cost, which is simple multiplication and sum. The absolute value here removes any negative numbers that might be introduced by the cost function. And this is because probabilities are only defined in the range 0 and 1. Next step is to calculate the new probability matrix, and this code is just the implementation of the algorithm shown on the right. So we initialize the step size alpha, which I ended up settling on a value of 0.95 after doing a few different tests ranging, and I noticed that I got the best results for an alpha between 0.8 and 1.2. So I start by calculating the eigenvalue of the probability matrix, and then calculate the subgradient of the eigenvalue vector. Next, I calculate the new probability matrix, and then clean it up because sometimes the gradient or the subgradient would result in having non-zero terms outside of the tridiagonal. Next, I report the final cost and stationary distribution. So the main program will output the stationary distribution, the total cost, and the cost savings in percent if any optimizations took place. The main program also accepts threshold and increments to set the granularity of the repeated runs. I'll go over this when we actually look at the MATLAB. Not all random vectors result in optimizable matrices, so to obtain good data, I decided to rerun the entire script on new initial probabilities until optimizations occur, just so I can verify that the code actually does work. So before I move into MATLAB itself, I'll go over some results and analysis. So I found that there are 3 main cases of outputs. The first and most common is that no optimizations occur for any cost function. And this makes sense because the inputs are random. So you can't always reduce the initial equation that was provided by the authors. The next possibility is that optimizations occur for both C1 and C2. You can see on the left that both C1 and C2 both decrease over time. Now this doesn't happen often, and the savings typically are less than 15%. Now what happens more often when there is an optimization is that C3 changes over time. And this one changes while the others don't because the cost increases as the length increases. I also found it interesting that the best results actually occurred for larger matrices, but the calculation takes much longer. Alright, so I'll go through 2 quick examples, just because the code can sometimes be a little finicky of when it actually gives valid results. So for the given initial probability matrix of length L equals 9, as shown below, we obtain the following stationary distributions, which, as I mentioned a while back, these are our queuing policies, with the following total costs. And we notice here that this is one of the cases where we have the first and second cost functions result in savings, while the third does not. Next example is for a following matrix of length 8, shown below. And we obtain stationary distributions as shown. And for the total cost, we end up with savings of 4% in case 3. From all my runs, I noticed that optimizations don't always occur, and this is actually the case more often than not. The total cost savings, when they do occur, are typically modest, less than 15%. Because of these two factors, I feel that this novel approach presented by the authors is not really a game changer because it's too inconsistent. In fact, when we move over to running the MATLAB code in real time, we'll probably see the line no cost reduction found trying new matrix several times before we actually see an optimization occur. From a runtime standpoint, it's most efficient for matrices with a dimension less than 10, but the algorithm is most effective for matrices with a dimension greater than 8. We often see that the smaller matrices often go through several full iterations before an optimization can be found. For future work, I'd like to determine how to turn an optimized queuing policy into a network, because the paper only goes one way. It abstracts a network policy as a queue. But once you have all this information, they don't really go into any detail on how to convert the optimization that we just obtained into a usable network protocol. With that said, let's move to the MATLAB. So first we'll look at my main script that executes all the functions that I discussed previously. We see here in line 4 that we'll continue to run the entire algorithm from start to finish, including all the iterations multiple times, until we have a cost reduction in any of the cases that is greater than 0. From lines 21 to 32, it's just a simple saving method, so I can report back the lowest total cost of all iterations and also store the corresponding stationary distributions. Alright, now let's run the code and see what happens. Start with the length of 4. It's nice and small. We'll run fast, but it may take several iterations. So here we see that it failed to find any sort of optimization, but then on the second try we actually got a cost savings of 15% for case 3. Now let's try a length of 8, which is closer to what I was seeing the best results with. Now this will take a little longer to compute each time. I found that stationary distribution is what takes the longest, and unfortunately that is in the algorithm, or the iterative portion of the algorithm, so it runs every time all the way through. What we see, we have the cost savings about 16% in case 3. I'll bump it up just a little bit more. 10 is about the limit for how long you want to wait for a calculation, especially when it fails several times in a row. Alright, so we didn't get to see cases 1 and 2, but I did have an example of both of those showing cost savings in the first example in the presentation. But we did get to see 3 different instances where case 3 was able to show cost savings for 3 different size probability matrices. And that concludes the simulation. Thanks for watching.